In this video, we are going to discuss the two-sheet hyperboloid, just like the hyperboloid that we just did with the one sheet, but now we're going to do two sheets. You can probably predict what that means, one piece and two pieces. Okay, so before we get to the graph and what it looks like, let's talk about how to tell that it is a two-sheet hyperboloid. The first thing, that it has two negatives. Unlike its first counterpart, the one sheet hyperboloid, it only had one negative. Okay, it also has all power of 2. And then also a constant. All right, couple notes. Just like the last time, standard form helps with traces. All right. The next note, always directed along, and it's always the odd person out, along the axis with the positive. Always the one that's not the same as the other two. Then we set positive variable equal to 0. Well, if we do that, actually, if you consider it, and you try to solve, there is no solution. Let me show you. That goes away if we let the positive one go 0. This is a negative, positive, negative, positive. So these two together are two negative numbers added together, which means it has to be a negative always. It will never be a positive one. So setting, just like the last one, or like the last one, setting it equal to 0 did something. This one does nothing. I've had students, I've caught myself in a lecture before where I tried to do that, then I was confused on why it gave me nothing. So that's if you're unsure why it does nothing, go ahead and try to set it, the positive variable equal to 0, plug a 0 in for it, the positive, the x up here, and try to solve, think about what shape that would be, or think about the graph itself, something like that. Just analyze the graph. Okay, so what would do something is if we set both negative variables equal to 0. This will give us axis intercepts. All right, and then the last thing for us to do to be able to graph this, we're about to go through the whole procedure. Set the positive variable equal to numbers. Oops, I don't know what that was. Numbers divisible by denominator. All right, so now we're going to get an example of one of these. All right, so here we go, next page. I am outside. It's really nice today, so if you hear a car, a honk, I live in between two highways in Tulsa, so forgive the traffic sounds if you do hear them, or birds or whatever. Okay, so first thing I'm going to do is I'm going to flop things around. I like the X to be up front. And then I'm also going to move that 9 over. All right, so from there, I would really like a positive 1 on the right, so I'm going to divide everything by negative 9. So I got negative x squared over 9 plus y squared over 9 minus z squared over 1 equals 1. Okay, and then I can move these around. Y squared up front minus x squared over 9 minus z squared over 1 equals 1. All right, let's confirm what it is. It has all squares. It's abbreviation for squares. It has one positive and then there's a constant, right? Those three things together tell us that it is a two-sheet hyperboloid. All right, so those things tell us that. So let's find our traces now. Okay, these were those instructions on the last page. So for intercept, right, we're going to let x equal z and let both of those be 0. This is going to give us our y-intercept. So we get y squared over 9 equals 1. That's letting x and z equal 0, which if we times by 9 and take the square root, we get y equals plus or minus 3. Okay, so I am going to graph those. That's all we have. On the y, we have plus or minus 3. That's it. Okay, so and then the next thing I'm going to do is we want to plug something into y that's going to be nice with this 9. So we don't want to do 3 because we already have 3. So we're going to pick something else. Well, the next number would be 6. And we're going to do plus or minus 6 because it's going to square it anyway and it doesn't matter. So if I plug that in, okay, if I plug 6 into y, right, I get 6 squared is 36 divided by 9 is 4. And then I get the rest of the equation. All right, I'm going to minus 1 and then add my terms over. So I'm going to get x squared over 9 plus z squared over 1. That was adding those over. Then I'm minusing 1 to the other side to get me a 3. If I divide by 3, that's just multiplying. So x squared over 27. That's what I mean by multiplying. We just are dividing. So we have this, which, okay, remember this is a squared. So that means the square root of 27. That's about 5.1. This is b squared. Take the square root of 3. That's about a 1.7. That's an ellipse. Okay, so I have an ellipse when y is plus or minus 6. So at 6, so I'd go out, and now I'm going to take these, I'm going to make some axes out here. So moving that out here. I also would like an up and down one. Right, and then actually I could do with one going this way too. There we go. Okay, so I'm going to add my tick marks, try to stay as straight as possible. So probably off, but it's okay. Okay, so let me go back to a red, because that's what we were graphing the other one with. This is an ellipse on the XZ plane. That's the one coming out at us. And it is about 5.1 in the X direction. Okay, so that means I need some more tick marks. All right, so that's about 5.1. And then about 1.7 in the Z direction. So here's my, okay, I have an ellipse here. Oops. Something like that. Okay. And then we can graph this exact same thing on the other side. So I'm going to go ahead, not erase, but I'm going to copy and paste. You guys can graph this on the other side. Just copy, paste. So you're going to pause the video and do that. And then we draw this coming out. So it's like this. I'm going to do the ones that I actually can first. And then the other ones are going to be dotted lines. Yep. All right, we get something like that. These like extend. These extend on. Right, and then this side, let's try to make it as clear as we can. That. Goes like that. Goes like that. So, yeah, that one's kind of harder to see. I messed that one up quite a bit. There we go. Maybe that's a little better. So you can kind of see what's going on. It's like almost like a parabola-like shape, extending out in each direction here, like a bulb almost, or a mountain, like two-dimensional mountains. I don't know why, or three-dimensional mountains coming on down on top of each other or something. I don't know, but there's like a gap in between here. But yeah. I think you said, let's take a look at an actual picture so you guys can actually get a full grasp of what this is supposed to look like. All right, there we go. So we have like almost like parabola type things. Let me try to stop it some way, I think. Let's try to get it the way we have it. Maybe like that. Oh. Something like that, yeah. All down. Yeah, there we go. This thing's kind of hard to move. I'm on an iPad too, so try it out. The GeoGebra thing, it's pretty good. Okay, so that's what it's supposed to look like. So this is a 2-sheet hyperboloid. Remember, this was a 1-sheet, and then a 2-sheet. It's 2. So see how they have the similar shapes. If I even put them, I can put them on top of each other like that, and you can see one's inside the other because of the numbers. But if you built it the same way and just made one, change the signs, that's it. Just make one positive, negative, they would fit, and there would just be a perfect in between. So what I mean is copy like equation 3 there, copy that down below if you're on GeoGebra, and change the plus where the 9z squared is, change that plus to a minus, and they'll fit right into each other. So yeah, one's literally 1 sheet, one's literally 2 sheets, 2 different pieces. So that is a 2-sheet hyperboloid and our attempt to graph it in 2 dimensions.